Welcome to Intro to Polynomials, video 2 of 3. So let's start the video by actually pausing the video and making some observations, all right? Do you notice anything between the degree of the function and how the graph looks? For example, I notice that as your degree increases, your graph gets more complicated, right? There's more squiggles, more turning points. So turning points increase as the degree increases. For example, your very first function goes in a straight line. There's nothing going on, right? But the last function, the quintic, which is the degree 5, turns around 1, 2, 3, 4 times. The cubic function turns around twice. So your function will turn around more and more as your degree increases. Do you notice anything about the degrees and what that means for the arrows? I noticed that all even degrees have arrows going in the same direction. So my quadratic, both arrows go up. Quartic, both arrows go up. They can also both go down, but in these examples they go up. Now my odd degrees have arrows that go in opposite directions, right? One's up, one's down, one's up, one's down, and the same thing. And that's going to hold true for all functions. Even degrees, arrows will always go in the same direction. Odd degrees, arrows, they got to be odd and be different, so the arrows go in opposite directions. Now we're going to fill out a chart. So first of all, the degree of a linear function we should know is a degree 1. The possible number of x-intercepts, let's imagine this red bar was your x-axis, is 1. Now hit the x-axis 1 time. Now there are no max and mins on a linear function, right? It goes up forever and down forever. There's no largest point or no smallest point. So that would be 0. We know quadratic functions are degree 2, right? Because this is a x squared. The number of possible x-intercepts is 2. Now I say possible number of x-intercepts is because it doesn't necessarily have 2 x-intercepts, right? Y equals x squared only has 1 x-intercept. It just has a maximum amount of 2. This one also has a minimum point. So it has 1 minimum, or if you see an upside down parabola, which is an upside down quadratic, it'll have a maximum. So it depends. Cubic functions are degree 3. The number of possible x-intercepts is 3, right? 1, 2, 3. Again, it doesn't have to have 3. It has a max of 3. Right here, it only has 2. If I move my x-axis down a bit, it only has 1. So it depends on what your graph specifically looks like. Now the number of max and mins, I see 1 max and 1 min. It's not the overall maximum point, but we call it a local maximum. Quartic functions, degree 4, maybe you'll see where this is already going, has a possible amount of 1, 2, 3, 4 x-intercepts. The turning points, you have a min, a max, and a min. So 3. Quintic functions are degree 5, x to the 5th. It has a possible number of x-intercepts. Again, we can assume this at this point. We should see a pattern emerging. It has a possible amount of 5. Not necessarily 5, but in this case 5. The number of max and mins, we have one max, a min, a max, a min, that would be 4. So if you notice, polynomials they have basic rules that's going to happen, patterns. So the number of possible x-intercepts is your degree. And we should know that from solving equations, right? If we had a quadratic, we knew we were getting 2 solutions, which come up as x-intercepts on the graph. But we didn't always get 2 solutions, right? Sometimes we had a double root, and we had 1 solution. Sometimes you could even have no solutions. So just keep in mind that the number of possible x-intercepts are up to the degree. The number of max and mins are 1 less than the degree. So let's look at what type of function this is, and you might know it just based on the shape. We know that it has to be an odd degree, right? Because your arrows are going in opposite directions. We have 1, 2, 3 x-intercepts. And we have 1 max, 1 min, so we have 2 turning points. So without knowing the equation, I can say to myself with this information, this is a cubic, because it seems like it's a degree 3. What type of function is this? Now you might know that this is a parabola, right? That this is a quadratic, just based on the shape. Now, this particular quadratic only has 1 x-intercept. Even though quadratics usually have up to 2, so keep that in mind. This also has 1 minimum. Now, if it has 1 turning point, and if your number of turning points are 1 less than the degree, 1 more than your number of turning points would be a degree 2. That lets me know that this is a quadratic. This one, no max and minimums, so there's 0 turning points. It's going to be linear. This type of function, I know it has to be an even degree because my arrows go in the same direction. I have 1, 2, 3 turning points, which means if you add 1, it is a degree 4, which means it's a quartic, which makes sense because a quartic is an even degree. This type of function, your arrows go in opposite directions, so you're going to have a odd degree. I have 1, 2, 3, 4 turning points. Well, add 1 and you get a degree 5. So it has to be a quintic. Okay, looking at the number of x-intercepts isn't always too helpful when looking at what type of function it is, because as you can see in this case, you only have 1, 2, 3 x-intercepts. Doesn't really help me. But using the turning points and the number of x-intercepts together, that might help you out in figuring what's what. So the same type of function can have a different number of x-intercepts, which we've talked about. For example, a cubic function could have 1, 2, or 3 x-intercepts based on the graph, right? The first one is 1 x-intercept. Next one has 2 x-intercepts. And then the last one has 3 x-intercepts. Okay? And this is x cubed, which we know is a third degree. So like I said, sometimes try to rely on the number of turning points. Now, why can't you sketch a cubic function with no x-intercepts? If you need to, pause the video and think about it. So if you notice, the arrows point in opposite directions, since it is an odd degree, right? Degree 3 is odd. At some point, it will cross over the x-axis. Even if you try to be clever and make a cubic that is like this. And you might say, oh, this doesn't touch your x-intercept. Sorry, it doesn't touch your x-axis. There is no x-intercept. This does go on. So even though it doesn't cross in your graph, you should know this extends and eventually crosses that x-axis. Pause the video and try to sketch a quadratic function with 0, 1, and 2 x-intercepts. There's multiple answers for these. So for the first one, this is what I drew, right? It's not touching your x-axis at all, and it never will because it's an even degree. So because the arrows both go in the same direction, even degree polynomials don't necessarily have to touch the x-axis. They don't necessarily have x-intercepts. Only odd degrees do, for sure. You could have also drawn one up here to the side or down here. Like I said, many answers. For the second one, this is touching your x-axis at a tangent, right? And that means it only touches once. So there is one x-intercept. Could have also drawn something to the side. And your last one, make sure it crosses over twice. Could have also drawn something like this. Now, what's important here is that it's a degree 2, right? So it has 2 solutions, even though you don't see the solutions on the graph. Right here, I can easily see 2 real solutions. Here, I see 1 real solution. Here, I don't see any x-intercepts, no zeros, no roots, no real solutions. But I'm going to say that it still has solutions. You just can't see it on the graph. And that brings us into real solutions versus imaginary solutions. So, an x-intercept is the same thing as a real solution or a real root. You might know this as roots, zeros, x-intercepts. Yeah. Now, the degree of the polynomial should be equal to the total number of roots, both real and imaginary. And you should know that imaginary roots always come in pairs. That's actually super important because the regions will try to trip you up, saying there's only one imaginary root, and you need to know that's not even possible. There are 2 imaginary roots. There can't be 3 imaginary roots. That's not a pair. It needs to have a buddy. There can be 4 imaginary roots, 6 imaginary roots, 8 imaginary roots. They have to come in pairs. They have to be an even amount of imaginary roots. So let's look at the first example. Looking at this, I know that the largest exponent means it is my degree. So for the first one, A, my degree is 3, because that's my largest exponent. So that means there's going to be 3 total roots, or sorry, 3 total solutions. My graph has 1 x-intercept. Now, It's one x-intercept with a multiplicity of 1. So that solution happens one time, which means there is only one real root. Now, if you know there are 3 total and 1 is real, that must mean that there are 2 imaginary that you cannot see. Remember, imaginary roots always come in pairs. So if you wrote 1 imaginary, definitely wrong. Are we okay with this? Try the next one if you are. Before you even start doing the next problem, you should notice that there are 4 total solutions. And if you read your answer choices, choice 4 only has 2 total, which is definitely wrong. So we have 4 total, and then we're going to look at the graph, and we're going to see 2 x-intercepts, both with a multiplicity of 1, which means there are 2 real solutions. So 4 total minus the 2 real means I have 2 imaginary that I cannot see on this graph, which would be choice 2. Let's talk about extrema. Now, local extrema is just another term for a turning point, which we've talked about in this video already. It is the maximum or minimum in its neighborhood. So it doesn't mean it's the largest point. It's just in that section of the graph you're turning around. So that would be an extrema, a local max we call it. Now the number of local extrema is 1 less than the degree, what we were noticing before. So when it asks you what degree of the polynomial graph is shown, you're going to go to the extrema. I have 1 extrema here, 2, 3, 4. So you have 4 extrema. Or if you want the less fancy term for it, it would be 4 turning points, which means you're going to add 1, and you're going to say that this is a degree 5 polynomial. You should never get tricked and choose choice 4. The reason is your arrows go in opposite direction. That means it has to be a odd degree. Figure out the degree of the polynomial on your own. Again, I know that this has to be an even degree because the arrows go in the same direction. And then I'm going to look at the extrema. 1, 2, 3 extrema plus 1 would be 4 as your degree. So now let's talk about end behavior. So end behavior is a way to describe what happens to the function as x approaches positive and negative infinity without having to actually draw the graph. So as x approaches positive infinity, we're talking about positive x values are to the right. Negative x values are to the left. So it's a fancy way of saying as your graph goes to the right, what's happening? As your graph's going to the left, what's happening? So in order to write end behavior, first of all, let's talk about where our positive and negative values are. So if you have your x-axis, let's say this is positive 10, and this is negative 10. You could keep counting to the right. You can go to positive 100, positive a million, positive infinity, right? You could count up forever. You can also go to the left more than negative 10. You could go to negative 20, negative 1,000, negative infinity. It just means negative x values are on the left, positive x values are on the right. Let's talk about your y-axis. Positive y values, like a positive 10, is up top. So you can say positive 10, positive 20, positive 100, positive infinity is up top. You could count up forever. Negative 10 would be at the bottom because negative y values are at the bottom of the graph. You could keep counting down forever until you get to negative infinity. So these 4 points, I want to use yellow. These 4 are always important because they'll help you out with what's going on. Now, when we're talking about behavior, you do need to remember that function notation. Instead of writing y equals, we tend to write f of x equals. So if they're talking about x, we're going left and right. If they're talking about f of x, you're going up and down. Now to write end behavior, this is a formula you are always going to start out with. As x, for the arrow we say goes to. So as x goes to negative infinity, what does that mean? You're going to look at your graph. As x goes towards negative x values are on the left. F of x goes to where? Now remember, this is talking about your y values. So y values do what on the left-hand side of the graph? On this left-hand side, we are going down. If you're going down, that's towards negative infinity. Now, as x goes to positive infinity, positive x values on a graph are to the right. So as x goes to the right, find the right side of your graph. It's heading up. So my y values are heading towards positive infinity. This whole answer, highlighted part, is what you have to write each time it's asking for end behavior. Why don't you try giving the next one a try? Start by writing positive x values, negative x values, positive y values, negative y values. And remember, this is f of x. So pause the video and try it on your own. So as x goes to negative infinity, negative x values are on your left. What's happening on the left side of this graph? It's going up towards the positive y values. So you're going to put infinity. If you'd like, you could put positive infinity. As x heads towards infinity, positive x values are on the right. So f of x on the right-hand side, it's going up as well. So you're going to say that this graph is heading towards infinity. Take some time to get used to. This entire thing is your answer. And on the regions, they're most likely not going to write any of it for you. So you do have to remember, anytime they say end behavior, automatically write as x goes to negative infinity, f of x goes to. As x goes to positive infinity, f of x goes to. That's what you start with. And these can be switched. You can start with x going towards positive infinity and x going towards negative infinity comes last. So it doesn't matter which one's on top or bottom. That is all for this video.